So we have been looking at linear modeling in the past few lessons, and now what we want to do is summarize this idea of linear functions. So we know that linear functions have a constant rate of change. To determine the constant rate of change, and another word for that is slope, we use the formula m equals the change in the dependent variable, which we usually call y, over the change in the independent variable, which we usually call x. So change in y over change in x, that little triangle symbol that you see here, delta y over delta x, that means change in. The triangle means change in. We want to be mindful of whether our slope is positive when I have an increasing line or a line that's going uphill, or negative when I have a decreasing line or a line that's going downhill. So a line that slopes, it doesn't really matter which one you start with, but I'm going to start with downward. A line that slopes downward from left to right will have a negative slope. So this line that slopes downward would look like if I have a person right here walking on the line, that person would be walking downhill. So the line is decreasing from left to right. A line that slopes upward from left to right, in other words, the line would be increasing, that will have a positive slope. So a positive slope will look like a line that if I have a person here on the end, far left, and that person is going uphill, then that line is increasing and the line is sloping upward. Okay, so when we talk about the rate of change rule, we want to realize what we mean by change. Change is an amount that is increasing or decreasing. So it's not like a final amount, but it's a difference in two amounts. So I'm going to first write this rule out in words, and then I will use symbols. So in words, the change in the dependent variable, which dependent variable would be the y, is equal to the rate of change, I won't abbreviate this time just so we're being thorough, times the change in the independent variable. And the independent variable is associated with the letter x. Independent, forgive my writing, change in the independent variable. Okay, so in symbols, what this is going to look like is delta means change in y equals rate of change is the slope, which we use the letter m, times change in the independent variable would be delta x. Now again, what we need to remember about delta change in, delta change in, is this is an amount that we are increasing by or decreasing by. It's not a final amount. So then this whole idea takes one step further to understand that when we model a linear relationship, if we want to write the full equation, then we need to make sure that we can identify our starting or initial value, which we denote with the letter B, and our rate of change, which we denote with the letter M, so that we can write our full equation in one of these two ways, y equals mx plus b, or y equals b plus mx. Again, m is representing that constant rate of change, x is the independent variable, y is the dependent variable. That always depends on the context of the problem. And then your b value is like our initial amount when x is 0, whatever the x represents. So in words, our y equals mx plus b or y equals b plus mx, we can think of it as the dependent variable is equal to the initial value plus the rate of change times the independent variable. So when we're looking at our full equation, the y equals b plus mx or mx plus b, we're no longer looking at increases or decreases in That is represented in the slope, but we're trying to determine what the y is when x is a certain value, or what the x is when y is a certain value. That is different than the change in x or the change in y. And you have seen both forms in examples throughout this lesson, throughout this section, and you will also see both forms in your homework. Okay, so now this is a generic graph that has a positive slope. How do I know we have a positive slope? I can see the line slopes upward from, I'm going to do a little abbreviating here, left to right. Okay, or I could say, hey, I have an increasing line. That's another way to say it. And when I have an increasing line, I have a positive slope. So again, this is generic. Delta y is the change in your dependent variable, which in context you'll be able to figure out, over delta x. And so this is just a visual for you to see what a positive slope looks like. You can see it. Another way, maybe you've heard before, is you're essentially determining the rise over the run. The rise is going to be the change in the dependent variable, and the run will be the change in the independent variable. So let's take a look at one example here where we will sketch a graph of this scenario, and then we will determine the rate of change. We have a price demand function. We have a small store that sells fresh pineapples. Based on the data for pineapples, prices are between $2 and $5. The store owners want to create a model in which a linear function is used to determine how the demand, which is the number of pineapples sold per day, varies with the price. Now, this sentence is important because you may not realize it's actually telling you which quantity is independent and which quantity is dependent. Because of the way it's worded, when it says the demand varies with the price, what we're essentially saying here is that my price is independent because the demand is going to depend on the price of the pineapple, okay? Pineapples. Because the demand is going to be the number of pineapples sold per day, and that's going to depend on how much these pineapples cost, okay? So demand is going to be on the y-axis and price will be on the x-axis. Then it says the owner finds that when the price is $2 per pineapple, the store, I see a typo, store can sell 80 pineapples per day. Okay, so we have 1 point that we could write as 280, and I'm going to be graphing that point in a minute because $2 is the price and then 80 is the demand. We can use the letter D for demand. We can use the letter Q for quantity, number of pineapples sold per day. And then I have another scenario here that says when the price is $5, only 50 pineapples can be sold per day. And this is because as the price increases, people are not going to want to pay a higher price, so the demand will decrease. So if I make this graph, I'm going to want to think about like how I want to scale my axes because I need to be consistent on each axis. So I'm just going to scale by $1 on the price per pineapple, or I'm sorry, the price of the pineapples. And then I need to go up beyond the 80, so maybe I count by tens here. So 10, 20, 30. This is number of pineapples sold per day. 40, 50, 60. I may have to increase this a little bit. You may have to also 70 and let's say 80. And again, maybe it goes higher than that likely. in terms of where your y-intercept would be, but in this problem, we're only trying to determine the rate of change after graphing this. So I'm going to plot a point now at 280, which would be here. This would be the point 280. So that's $2 per pineapple. The store sells 80 pineapples in a day. And then I have 5 and 50. So this would be 5 and 50. That's $5 per pineapple, selling 50 pineapples per day. And then I want to connect these with a line, straight line. Again, you can see that that is your y-intercept, or your initial amount, if we were determining it, would be higher than the 80. So if they were free, you're going to be able to sell more than 80 a day. You'd be giving them away. So that would be the graph of the scenario. Notice that we want to label our axes, we want to scale each axis, and we want to include all of that in our work. The next thing we have to determine is our rate of change with units. So this is going to be our slope. Change, and I'm going to use words here. Change in Y is going to be the change in demand. So delta demand over the change in X will be the change in price. So when we include our units are going to be pineapples per dollar. And we're expecting this to be negative because we can see that our line is sloping downward. So what I'm going to do to determine, there's a few ways I could do this. I could do this on the graph, but it's hard because I sketched this. But this is essentially going to be the change in demand. So to figure that out, that's going to be 80. Actually, let me write those the other way around. Let me go from the second point to the first point. So I'm going to go 50 minus 80. And then my change, so this will be my change in Y. This is going to be my change in X, which I find by subtracting. So my change in price, second point to the first point, will be 5 minus 2. If I simplify my numerator, I get negative 30, and this is pineapples. And then over 3, and this is dollars, a change in $3. And so if I simplify this, I'm going to get negative 10 pineapples per dollar. You could use a dollar sign there, and I expect that this will be negative. It is not negative $10 per pineapple, so it's really important that when you write your units for the rate of change, you have the change in Y over the change in X. So in this case, it's negative 10 pineapples per dollar. So essentially what that means is for every dollar that I increase the price, the demand is going to go down by 10 pineapples. For every dollar that's increased in price, the demand will go down by 10 pineapples. So that's sort of the meaning of that rate of change. Contextual problems can be tricky because it really does depend on how the problem is worded for you to decide what the independent and dependent variable is. And that's an important step to making sure that you are graphing the correct graph and determining the correct rate of change with correct units.